In this video we're going to make some plots illustrating the distribution of prime numbers. So we're going to import the usual sort of libraries. Now we're going to we first need a function which will find primes for us. Okay, so we're going to do a function that finds the list of primes up to some given number n. So we're going to start with an empty list of primes. Okay, so then we're going to walk through the numbers from 2 up to n plus 1, and we're going to try and see which one of them are prime. Okay, so we've got a number I, and we want to know whether it's prime or not. So we just have to check whether it's divisible by any of the primes that we found already. Okay, so we look through the primes that we found already. Okay, then we're going to check whether I is divisible by p. So we can do that by doing I % p or I modulo p. So I is going to be divisible by p if and only if I % p is 0. And if it is, then we can break out of this inner loop where we've. That means that it's. Okay, so actually let's be a bit more explicit about this. So okay, well we're going to say that I is prime, right? As far as we know, it's prime. So we're going to sort of say that it's prime until it's proven otherwise. And so now, if we find that there's a divisor, then we're going to set is prime to false. Okay, and then we're going to break out of the loop. We don't need to test any more primes as soon as we found one. One prime that divides I, we know that I is not prime. Okay, so now if we get to the end of the loop, so we haven't found any divisors, so this means that I must be a new prime. So we just do we can add I to our list of primes. Okay, and then once we get to the end, then we return the list of all the primes that we found. Let's just check it's all okay. So you can find the primes up to 20, 2, 3, 5, 7, 11, 13, 17, 19. That's kind of easy enough to check that's okay. Okay, so for our purposes, we're going to need we're going to need the first 100 primes. So let's look at the primes. 25 primes up to 100. Up to 200 we get 46. Let's go up to 400 maybe. We've got 78. We want to try and get 100 primes. So let's go to 600. 600 is too high. 550 is just a tiny bit too high. Let's try 540. 545 maybe. So that gets us 100 primes. That'll do. Okay, so let's plot them. Okay, so what are we doing here? So the x coordinates are just numbers. Yeah, so length of the prime list is actually going to be 100 here. So I could just have put in 100, but it's better to do it this way so that if I change the prime list, then it will also just check again and find the length of the relevant list. So yeah, so the x coordinates are just numbers, 0, 1, 2, 3, etc. and then the y coordinates of these prime numbers. So we get this kind of rather wiggly line here. Let's kind of plot it as separate points. So if we do, that's a kind of trick in Matplotlib. We can, if we do this, if we do it with an O here, then it will print it as blobs. If I do it with a dot, then it will print it as rather smaller blobs. But if I do it with a comma, it'll do the smallest possible blobs. These are just single pixels. Okay, so you can see there's a little dotted line here consisting of these single pixels. And so this kind of looks quite regular, and you might ask yourself whether there's actually a formula for it. And it turns out that there's not really an exact formula, but there's a good approximate formula for what the nth prime is going to be. So let's put this in here as a separate thing. Okay, so approximate formula for the nth prime. So this is something you can learn about in a course on analytic number theory or something. Okay, so we you get n, but then you multiply it by this thing here, which is log n plus log n minus 1. Okay, so okay, so there. So it says the approximation to the nth prime. Of course, this isn't actually, it's not actually forced to be an integer. So it's saying 513 is the approximate value for the 100th prime, which is, and then we can do actual 100th prime is the minus first entry in the prime list, which minus 1 means the last entry, so that's 541. Okay, so it's kind of reasonably close, but not super close. So let's actually plot these two things in the same graph. Okay, so actually, let's go further. We'll do so we'll do the first 1,000 primes instead. It works out that 7920 is the appropriate thing to do there. So we're going to be precise here, this nth prime thing, that's the kind of nth prime starting with 1, so we should plot against the range 1 up to 1001 rather than 0 to 1000. Okay, so that, and then we're also going to and the approximate prime thing doesn't really work. If we start at 1, we have to start at 2, so we'll just do that, and then okay, so that's our approximate primes, and okay, so then let's so yeah, we're going to plot these little dots are the actual values of the primes, and then this red curve is the prediction from this nth approximate prime function, and you can see that they're not exactly the same, but they're very close. So that's part of what's called the prime number theorem, out the approximate distribution of primes.